This is Precalc, Chapter 3.4. We're going to talk about complex numbers today. Guys, you've been working with complex numbers since Algebra 2. Nothing new here today. Nothing at all. Tomorrow, we're going to start to use this to find the zeros of those polynomials that needed this. But they go into complex numbers. You guys should understand that the reason we came up with complex numbers in math is because there are times where there are quadratic equations that came out to not so nice answers. And we needed a way to deal with the fact that you're going to end up taking a square root of a negative. And so they came up with complex numbers where they use I is equal to the square root of -1. Therefore, if I square both sides, I squared is equal to -1. So that's the basis of all of this. And we should also realize that a complex number can have a standard form that all numbers can be written in, and that is a plus bi. A is the real part, b is the imaginary part. Notice that I did not say bi is the imaginary. It's b. The thing in front of the I that's attached to it. That's the imaginary part, okay? So, I've got 4 examples down there. One with nice numbers, one with fractions, and couple of them with missing pieces. And I tell you what the real part is, what the imaginary part is. When we have 3 plus 4i, 3 is the real part, 4, which is on the I, is the imaginary. But when I have 1/2 minus 2/3 I, 1/2 is the real, -2/3 is the imaginary part. That's pretty straightforward. All the pieces are there. But then you come down to this point where it says 6i. Well, now you're like, wait a minute. I'm missing pieces. I'm missing the real part. And so if we're missing the real part, I say, hey, the real part's 0. It's really 0 plus 6i. And 6 then is the imaginary part. Vice versa, if there's no i's in it, like most of our real numbers, or all of our real numbers, -7 is the real part, the imaginary part is a 0. We just don't write it anymore. They also will call 6i, or something that's just the imaginary part, purely imaginary. So that means it just has imaginary pieces. By having complex numbers, we now are able to complete the study of the solutions of any polynomial equation, from quadratic to whatever we decide to have a degree of. The book also states, and it's important to know, that just because we call it imaginary doesn't make it any less real, in the sense that it does come out to be a solution as any other number. We have real, we have imaginary. Real solutions are real because we have the real numbers. Imaginary solutions are still solutions. We just call them imaginary solutions because we're using I. But they're just as much of a valid answer as 2 or the square root of 3 or something on those lines, okay? It's kind of important. Can I move on? So the first thing that we're going to talk about with all of this is the arithmetic operations on complex numbers. You got to still remember that I squared is equal to -1. But we're going to add, we're going to subtract, and we're going to multiply these. They work just like any irrational number when added, subtracted, and multiplied. It all comes down to, when you add and subtract, like terms. When you multiply, you got to make sure that if you are multiplying a square root times a square root, the square root can disappear. In this case, if you're multiplying I times an I, the I disappears, becomes -1. Okay? So the biggest thing that you're going to notice when adding, subtracting, and multiplying is how they state their answer. It's no big deal, guys, if I have whole numbers for A and B, C and D, because a whole number plus another whole number becomes just a whole number. It's nice, or integer. So your answer still could come out to something that looks nice. But if it doesn't, what if C happened to be an irrational number, like a square root of 2? Then it's perfectly fine as an answer to have something like 2 plus the square root of 3 plus 4 minus the square root of 5i. What they will do, especially when we have complex numbers, is they group things together so that we can say, hey, this is A and that is B. They need to factor out I. You group the I stuff together and take it out the back. Poke an I out sometimes if it has a square root of a negative number. Things that you guys should have all talked about. And guys, some of us are getting hung up on the fact that, hey, up here I'm just gathering like terms. I get rid of parentheses and then I can gather like terms. Usually that means there's a number out front of the parentheses or a negative. Got to distribute. But when you multiply, you can't forget your 4-letter F word, FOIL, when it's a binomial times a binomial. This is the only one where you guys would have to use the little rainbows and connect them together to multiply. Okay? When you're adding and subtracting, just gather like terms. Can I turn the page? Get some examples going. Okay. I want you guys to try all 4 of these, and then we'll come together and let people give it a try. All right.
I'm writing right now.
You are writing now.
Am I on?
Live.
Oh, baby. Okay, so that's right there. And then you just combine these two terms to get 7. And then you combine these two terms to get 3i. Oops. Come on. There we go.
Now, what if I said I agree? What some other things that we could possibly do here, thank you, to maybe make this a little bit clearer on what Jackson did. Drop the parentheses maybe on your first step. Understanding what's outside of those parentheses. There's something out there. There's something out there. There's a sign, but it's a 1, right? And 1 times anything is that thing. So that's why we could just forget about them and then add like terms. Who has part B? Okay, you're recording.
So first we will drop the parentheses. So 3 plus 5i minus, oh, that was really bad. But you have to remember that this negative also goes with this 2i. So you get 3 minus 4, which is negative 1. And then 5i minus negative 2, which is a positive 7i.
Okay. Now, I think everybody should agree with the answer. Mm-hmm. Does everybody agree with the supporting material?
No.
The way she has it written, I don't know if I could say that. She explained what she was going to do. But remember, when you distribute that negative, I would have wrote that as plus 2i. Instead of trying to think it through, automatically write it, because now you just have to gather like terms. Okay? Next. Yep, show us work, yep.
Okay.
You should be able to write.
So you're going to FOIL it. So you do the first. It's 12. Inside is plus 20i. Yeah. Okay. And then that. Negative 6i. And then last is minus 10i squared. But
I squared is a negative 1, so just be plus 10. Do you want me to write all that?
I probably would write it out and
Okay.
then fix it in the next line. Again, this is me trying to show everything.
Okay. And then you would just add like terms eventually. But I'll show the intermediate step. So then you have 12, 14i will be plus 10. And then 22 plus 14i. I think.
You think? Does everybody agree with I think? No? I do believe this would be right. Making sure that I squared is equal negative 1, so negative 10 times negative 1 is the positive 10. That is the right approach. Okay. I to the 20th power. Explain what you're going to do.
So, like, first I did I to the 22nd, and then I did I, because if you add them together, then you get I to the 23rd, or when you multiply them, I mean.
I like that.
And then I think, so, like, if it's even, it's going to be the negative 1, like I squared is. And then I is the square root of a negative 1. So then, or that's just I too. So you just get a negative I think.
How did you just all of a sudden go from I 22 is negative 1? So I don't like to necessarily we can say that because I squared is negative 1, but is I to the 4th negative 1?
Maybe not, I don't know.
Because that would be I squared times I squared, right? I mean negative 1 times negative 1, which would actually be 1. This is right. It becomes negative I. What if I said that Ashley needs to put one more step in there?
I would believe you.
What if we're gonna go over here. What if I broke up I to the 22nd power into that whole idea that I squared's in there? Isn't that I squared to the what power?
11.
To the 11th power times I. And I squared is negative 1 to the 11th power. Well, negative 1 to an odd power is negative 1. So negative 1 times I, which is negative I. So we get negative I. Okay? Through the process, what happens here is that we should have shown a step in between going from I 22 to negative 1. Just happened to work this time because I to the 4th power is actually negative 1 times negative 1 because of I squared times I squared, which is actually 1. You guys could have as well set up I to the 0, I to the 1st, I to the 2nd, I to the 3rd, I to the 4th, 5th, 6th, 7th, and you could have hopefully recognized as a pattern. That pattern that repeats itself every, I think, 3 or 4 terms. And you could have figured out where does 22 lie within that pattern. So that's an option too. Very nice. The last operation that we didn't talk about is division, dividing. So when you divide a complex number, guys, it's just like rational expressions. And so you need to rationalize the denominator. Think about it. I is a square root. It's a square root of negative 1. So therefore, I don't like it in the bottom. So I'm going to treat it just like multiplying a rational expression by its conjugate. I now multiply it what I call my complex conjugate. So what they're doing here, just to highlight this fact in that first paragraph, sentence or two, is they let z itself equal a complex number. And they say that then it has a complex conjugate, z with a little bar over it, of a minus bi, because the original is a plus bi. That'd be no different than if I would have had something like not a, but 2 plus the square root of 3. Its conjugate would be 2 minus square root of 3, right? And this time, instead of the square root of 3, it would be a square root of negative 1, which is I. So you could have 2 plus I, then you would have to have its partner of 2 minus I. Okay. The coolest thing about it is when you multiply the conjugates together, you end up with a squared plus b squared. And that ends up getting rid of any i's because I squared equals -1. Notice that's not the difference of squares, it's a sum of squares. Because of the I squared turns it positive. So they just kind of go through the steps here showing all of that if you had this complex fraction, right, that you just multiply the top and bottom by its conjugate of the bottom. Which leads us to this weird looking thing that could be complex looking, but it's not a complex fraction because that would have fractions within fractions. So we don't have to worry about that. Just looks complex. Notice the questions are asking us to rationalize, or not rationalize, rationalize really, the complex part of this out, and then write it in the form of a plus bi. I'll give you guys a couple seconds, and I'll let someone try this. And we're going.
Okay. So we got to multiply it by 1 plus 2i.
To the top and bottom.
Yep, to the top and bottom. And then we're going to FOIL the top. 3 times 1 is 3. 3 times 2i is 6i. 5i times 1 is 5i. And then 5i times 2i is 10i squared, which is, which is actually -1, so it's minus 10. And then we have, off of that, how can I, okay.
Oh, you can zoom in.
Oh.
Pinch with 2 fingers.
Okay. Okay. So then we have, off of that, -7 plus 11i. And then, not really know how to move this. And then we have the bottom, we can also FOIL 1 minus 2i. That over times 1 plus 2i. Oh no. I don't know. It just happened. What?
On the screen. Left. One more time. Oh wait, sorry. No. There you go.
Okay. And the answer to that is, okay, I'll go through it actually. 1 times 1 is 1. 1 times 2i is 2i. Minus 2i. And then 2i times 2i is 4i squared, or minus 4i squared. That becomes -1, and so that comes out to 5. Kind of going all over here. And then the answer ends up being -7 plus 11i over 5 equals, that's, do you want me to like go one step further?
Yes,
Okay.
it does say put it into
Simplest
standard form.
Okay. So we got -7 over 5 plus 11 over 5i.
Okay. I do believe that went correct. So we got first hour. So, guys, the biggest thing when we're doing the conjugates would be to multiply the top and bottom by this conjugate, and then most likely using the 4-letter F word, and that is FOIL. So, any questions there? biggest thing, guys, for part B, we're not going to do it, but in part B, what would be the conjugate of 4i?
Negative 4.
Just negative 4i. So you're happy, guys, when you can just use i's. I'll let you in on a little secret. You wouldn't necessarily even have to use negative 4i. You wouldn't have to use negative 4, or you wouldn't have to use 4i. What's the only culprit on the bottom? Is I. How do I get rid of I? Just multiply by I. So technically you could go as far as just multiplying the top and bottom by just I. That'll get rid of it. Now, if you happen to use a negative 4i over negative 4i, you will eventually have probably an extra 4 or maybe even a negative 4 in the top and bottom that you would have to cancel out. You always reduce anyways, so in this case, it would not matter. This slide is important because it just explains, guys, that there's a principal square root, which is the positive square root of a negative number, but you need to also realize that there are two answers when you square root a negative number, just like there are two square roots when you square root a positive number. You get plus or minus the square root of r, or in this case, negative r, which means you can poke an eye out, and notice that they also like to write I in front of the square root. I generally put it at the back, but here's the problem when you do that, is somebody might do this. And you can't put I inside a square root. And so you would need to realize that the I is on the outside. So to fix that, they write it in front. Okay? Now, I wanted to put this slide in here because that should be kind of well known, the whole square root thing. But this idea, do you guys remember that if I have a square root of something like 2 times the square root of 3, that'll equal the square root of 6? Because you could take, when you have square roots, take the numbers and multiply them inside. Guys, that only works with their positive numbers. This is not true when they're both negative. It doesn't work that way. So therefore, this does not equal the square root of, well, negative 2 times negative 3, which would be the square root of 6. That does not work. To multiply square roots, you need to poke an eye out first, which means this becomes I times the square root of 2 times I square root of 3. Now you can say, hey, wait a minute, that's I squared times the square root of 2 times 3, which is negative 1 times the square root of 6, which is negative square root of 6. That's the proper way to do that problem. You can't cancel out the negatives. Not a good idea.
So it doesn't have to be plus or minus I squared.
These are the last things that we need to talk about with complex numbers. I am not going to go into all of these. Solving a quadratic where the answers are not real, they're imaginary. This is why we needed complex numbers. I think part A is pretty easy to solve because it's just got an x squared term plus 9. I think everybody could easily, quickly say, hey, I'm going to subtract 9, so x squared equals negative 9, and then I take the square root. But don't forget, in this case, that's writing plus or minus, so x equals plus or minus the square root of negative 9, which equals plus or minus the square root of 9i, because I poked an I out, and the square root of 9 is, so you get plus or minus 3i. Imaginary numbers, guys, come in partners. One positive, one negative. Now, that's great when it's like that, but when I look at B, I'm like, I want to just factor that thing. I don't want to go through any other hoops. But the only problem is, are there factors of 5 that can give me a 4? You're like, yeah, 5 and 1, right? But unfortunately, they're both positive, and if 1 and 4 are both positive, I end up with what? Or 1 and 5 are both positive, they end up with 6. That doesn't give me a 4. So it's not factorable, and when you have a quadratic that's not factorable, you would default to what, most likely? The quadratic formula. And if you use the quadratic formula, the same thing for the problem down below here. If I use the quadratic formula or completing the square, I'll end up having 2 imaginary solutions. So instead of me doing these problems, because you guys should know that already, what is the quadratic formula? X equals, it's always X equals, opposite of B plus or minus, B squared minus all over 2A. You guys should be able to handle that. We've been using the quadratic formula. It's just now, when your square root will have a negative value inside, poke the eye out, you're good to go. Okay, homework from chapter 3.4 on page 298, 1, 13, 16, 22, 29, 42, and 60. That is one of every type of problem that we covered today. Have a great day.